Hello and welcome to Math with Mrs. Becker. Today in calculus, we are going to hammer through section 2.3, which really focuses on the first and second derivative test, as well as get us ready to start sketching some curves. Well, first off, why do we want to sketch a picture of a function? There are a couple of really good reasons. The first one, a geometric picture of a function, it's often easier to comprehend than its abstract formula. And what they mean by that is if we have a function, if I give you a visual representation, if I show you what its graph looks like, you'll be able to instantly tell me things like intervals of increasing or decreasing, maximums, minimums, intercepts. There are things that you will be able to tell me. If I give you just an equation, it's kind of hard to figure out what the heck is going on, okay? So that picture really helps us comprehend what's going on. The material that we cover in this section is really just to get us a solid foundation. We are moving into applications, things like, when in real life do I really need to know how to do this, okay? We will get into that when we get to sections 2.5, 2.6, and 2.7. So now in 2.3, we just really want to get a good foundation, a good understanding of what's going on. So let's start this party. A sketch of a graph of a function. It has to convey the general shape, okay? Notice that it's sketch. It doesn't mean that it has to be perfect. We want the general shape of the graph. Things that you should have. Show where f of x is defined, okay? So make sure that if you have like a restricted domain, that you stay just within the values that are defined. We show where f of x is both increasing and where it's decreasing. And we looked at that earlier in this chapter. It should indicate where possible, sometimes it's kind of tough to do this, but it should indicate where possible, where f of x is concave up and where it's concave down. Okay, and that, remember, was based off of our second derivative, and that's what we will look at further today. One or more key points should be accurately located. So other things that you want to show besides where is it defined, increasing, decreasing, concave up, concave down. The other points that you want to include, if you can, are any extreme points. And remember, extreme points are maximums, minimums, and they can be relative or they can be absolute. Inflection points. And remember, inflection points, it's the exact moment that it switches from concave up to concave down or vice versa, okay? And any intercepts. And those can be x-intercepts, they can be y-intercepts. But putting all of this stuff together, you're going to get a pretty darn good shape of the graph. And this is not, none of this information is new. We're just looking at it in a different way, okay? So if you're like, yeah, that's a lot of information, what do I do first? How do I start? That was always my question back when I was in calculus. Like, you hear that and it sounds like so much. It's like, oh boy, I like the step by step. So those of you who think kind of like me, first off, I am sorry. Next thing, I did go ahead and kind of give you step by step what we do, okay? So you are given a function. Your first step, go ahead and compute the first derivative and the second derivative. With every single problem, you will need both. So you're starting with f of x, step one, find the first derivative, then go ahead and find the second derivative, okay? Now remember, the first derivative, it tells you the slope. The first derivative focuses on the slope, or that steepness of the line, okay? It tells us the intervals of increasing and decreasing. So if you're looking for intervals of increasing and decreasing, that first derivative is going to help you. If your first derivative is equal to 0, that's where you have possible extreme points. Where your slope is 0, that's where you possibly, there are times where you don't, okay? There are times where maybe you don't have a maximum or a minimum. But if you do have a slope of 0, that's where it's possible that they could fall, okay? If you're like, I need a picture, 152 in your book has some really cool illustrations. So again, you would go ahead and do this. Focus on the slope, increasing, decreasing. See if you have any maximums or minimums. Sketch your findings. Now we go to the second derivative. Second derivative tells you your intervals of concavity. So concave up and concave down. How is that curve going to open? When your second derivative equals 0, that's when you have possible inflection points. Now remember, if your graph does not switch from concave up or down, vice versa, you won't have an inflection point. Okay, that's why it says possible. Then we sketch what we find. Then we consider other properties of the graph. Things like intercepts. Sometimes those are the easiest things to find. Okay, so intercepts x and y, and you go ahead and complete the sketch. So the first derivative test, this helps us find extreme points because it checks for intervals of increasing and decreasing. The point where it switches, that is your extreme point. So suppose that you take the first derivative and you set it equal to 0. From there, you can solve for whatever your variable is, okay? If it changes from positive to negative at that point, let's say a is that x value. If it was positive, that means it was increasing. Then after that point, if it goes to decreasing, then you have a relative or a local maximum. If it was negative, then it hit that point where it was 0, and then it was positive, that means at that point is a minimum. If it does not change, maybe it was going up and it hit a flat point and then it went up. That has no maximums or minimums, but at this point right here, it might have a slope of 0. So this is an example of what it could look like if you do not have any maximums or minimums. So that's called the first derivative test. So let's go ahead and just look at just the first derivative at this point, okay? When the first derivative equals 0, that's a possible extreme point. Okay, I think the easiest way is to go ahead and use what's called a variation chart, and I'll show you what that is in a minute, okay? Step 1, if I have f of x, and I'm just going to rewrite it, because sometimes it just kind of helps me to focus. 1/3 x cubed minus 2x squared plus 3x plus 1. If I am applying the first derivative test, what I'm doing is step 1, you need to find the first derivative. You can't do the first derivative test without the first derivative. 3 times 1/3 is 1. You'd still have an x, reduce the exponent, that becomes x squared. 2 times -2 is -4. Reduce the amount of x's by 1, plus this is a 1. 1 times 3 is 3. I would no longer have an x. The derivative of 1 is 0. Now, in order to do the first derivative test, you set the first derivative equal to 0. So in our case, it's x squared minus 4x plus 3 equals 0. I have 2 possible extreme points. I know that because I have a degree of 2. I can factor this. 2 numbers that multiply to positive 3 and add to a -4 would be -3, -1. So my possible x values, if I take x minus 3, set it equal to 0, I'd have to add 3. If I take x minus 1, set it equal to 0, I would have to add 1. So now to see if they are maximums or minimums. Now here, let's check 3. So there's 3. This is my variation chart. We know that this is 0. The slope of this is 0. So I try a point to the left and a point to the right. So if I try 2 and 4, I want to see if the value, if I plug it into the first derivative, if it's positive, that means it's increasing at that point. If it's negative, it's decreasing. So if I put in a 2 into the first derivative, 2 squared minus 4 times 2 plus 3. This is a -1, so it's decreasing at that point. This has a slope of 0. Now if I put in a 4, 4 squared minus 4 times 4 plus 3 is 3. So it's increasing here. So what we just did, this is decreasing, this is increasing. I know that because of the signs. So it was going down, it hit this point where my slope is 0, then it's increasing. So we have a minimum at x equals 3. Okay, now to check the 1. 1 is right here. Okay, that's where the slope is 0. So that's where we have this, okay? We want to see if it's a maximum or a minimum point. So I need to pick a point to the left and to the right. So I'm going to try 0 and 2. If I plug a 0 into the first derivative, this ends up being a 3. Okay, so what happens is my graph is increasing at this point. It hits this. 2, we already plugged in a 2. If I plug in a 2, I get a -1. So this is going down. It's decreasing. So it was increasing up to that point. It hit the 0. Now it's decreasing. So we have a maximum at x equals 1. Now here's the deal. We know that we have a maximum. We know we have a minimum. This is what a little variation chart looks like. It almost looks like an XY table, but what you're doing is testing points to the left and the right of where you know the slope is 0. They want us to find the points. Points is a key word for, hey, guess what? We need both x and we need y. We know the x's. Anytime you know an x value and you need to find a y, you always go back to the original. So if I have 1/3 times, my x is a 3. 3 to the power of 3 minus 2 times 3 squared plus 3 times 3 plus 1. This is 1. So we have a minimum, a relative minimum at 3, 1. Now I can go ahead and just up arrow, change all of the x's to a 1 because I know that my maximum is located at x equals 1. There are 3 places within this function that I have an x, so I need to make sure I change all of them to a 1. And I have 1 and 2 and 1/3. That's where the maximum is. So you guys, that's what the first derivative test is. You use the first derivative to find out where you might have maximums and minimums. To do that, you take the first derivative, set it equal to 0, solve for x. Then you do what's called a variation chart. This is where the slope is 0. So you have to try points on either side to see if it's increasing or decreasing, because in order to have an extreme point, it has to switch. Like here it was decreasing to increasing. Here it was increasing to decreasing. That's where you have your maximums and minimums. Okay, let's look at another one. This is going to be the general power rule. Here is f of x, our original function. I have 3x minus 1 to the power of 3. Okay, my first derivative. This is the general power rule because I have an exponent on a group. So the 3 comes out front. I keep 3x minus 1 the same. Reduce the exponent by 1. Then you multiply by the derivative of the inside, which is a 3. Now I can go ahead and multiply these two. So I would have the first derivative, 3 times 3 is 9. 3x minus 1 squared. So there's the first derivative. If I am trying to find maximum and minimum points, what I need to do is take that first derivative and set it equal to 0. We want to know when the slope is 0. So I go ahead and 9 times 3x minus 1 to the power of 2 equals 0. Step 1, divide both sides by 9. 3x minus 1 to the power of 2 equals 0 minus 9 is 0. Take the square root of each side. Square root cancels a square. 3x minus 1 equals plus or minus. There's no such thing as a positive or negative 0. The square root of 0 is just 0. So now to solve for x, I would have to add 1, divide by 3. So I have a possible maximum or minimum point at 1/3. Okay, now to see what it's going to be. This is 1/3. If I go to the left of 1/3, I could have 0. If I go to the right, I would have 2/3. Okay, so you want to make sure that you have a value that's smaller and a value that's larger. Right here, this is where I have a point and the slope is 0. Okay, that's what that middle line is. If I put a 0 and you're always filling it into the derivative. So if I have 9 times 3 times 0 minus 1 to the power of 2. I have 9. 9 is a positive value, so that means going up to that point, it was increasing. Now if I want to change that to 2/3, I'm going to go 2 insert, I want it to be a fraction, and I need to insert, there we go, 3 times 2/3 minus, perfect. Okay, when I do that, whoa, I got a 9. 9 is positive, so it hit here, and it keeps increasing. So this is kind of like what happened when I showed you this. It was increasing, it hit a point where it kind of evened out, and then guess what? It just kept increasing. That's what happened here, guys. So this has no extreme points, and I wanted you to see that. That's why in the front it said, if possible, find any maximums or minimums. So even though we did the process correctly, we found the first derivative, we set it equal to 0, we found our x, when we did this little variation chart, when I was looking at both sides, it was doing the same thing. In order to have an extreme point, it needs to switch from increasing to decreasing or decreasing to increasing. You do not have an extreme point when it goes from increasing to increasing. Okay, I hope that makes sense. That's the first derivative test, helps us to find maximums and minimums. Now the second derivative test, that helps us find, number one, it confirms our extreme points if they're maximums or minimums, which is so cool. And then it helps us with concavity. So what they're gonna teach us, if I have a point and its first derivative equals 0, okay, that means that it has a slope of 0. Your second derivative, this tells you concavity. If the second derivative at that value is less than 0, meaning it's negative, it's concave down, which means at this point is a local maximum. Okay, now check this out. If I have a point and its slope is 0, okay, so I have a horizontal slope right here. If you do the second derivative and put in that value, if the value is larger than 0, it's positive, that means it's concave up. If it's concave up, that makes this point a minimum. Check that out, super cool. So yes, we just did the first derivative test and we had to go ahead and use variation tables and figure out what was maximums or minimums. They're saying, yo, if you can find a second derivative, you can figure out if it's maximums or minimums using concavity. Okay, so we're just taking it a step further. Find and graph one relative extreme point. Okay, so we're going to use the first derivative test and the second derivative test. So put on your seatbelt. Here's my first function, just the original. 1/4 x squared minus x plus 2. First derivative. If I take 2 times 1/4, that is 2/4, which can be reduced to 1/2. I had 2 x's. If I reduce 1, now I'm down to 1. Minus, now this is like a 1. 1 times 1 is 1. I no longer have an x. This would be 0. Second derivative. This has an exponent of 1. 1 times 1/2 is 1/2. I had 1x, so now it's gone. The derivative of a constant, the derivative of a constant is 0. So I have my original function, my first derivative, my second derivative. Awesome. Now to find out where we might have an extreme point. First derivative equals 0. 1/2 x minus 1 equals 0. So if I add 1, 1/2 x equals 1. Then what I can do, you can't divide by a fraction. So what you have to do is go ahead and multiply by the reciprocal. 1/2 of 2 gives me just 1x. 1 times 2 is 2. So we may have an extreme point, whether it be a maximum or a minimum, at x equals 2. So now to see if it's concave up or down. So right now what we have is we know if we go to the right 2, and if I want to find out exactly where that point is, I can go back to the original. So if I go 1/4 times 2 squared minus 2 plus 2, 2, 1. So if I go to the right 2, up 1, that's where this point is, okay? I want to know, is that a maximum or is that a minimum? So now I use the second derivative and I fill in x. So if I go ahead and I go to fill in 2. Well, there are no variables. What this means, because this is a positive value and it's a constant, this thing is always concave up. It's up because it's positive. So this means that this is a minimum point because it's at the bottom of the curve. So this is always concave up because that's a positive constant. That makes this curve right there concave up, which in turn makes that a minimum. Boom! Mind blowing. Guys, this is a fun one. I wish we were in person doing this, but that's all right. We got this. Okay, second derivative test again. Locate all the possible relative extreme points. To do that, first derivative set it equal to 0. Then check the concavity. Oh, to do that, second derivative. So again, you're given a function, x cubed minus 3x squared plus 5. Step 1, go ahead and find your first and second derivatives. This is 3x squared minus 6x. Second derivative, 6x minus 6. Okay, now to find possible extreme points. First derivative equal to 0. 3x squared minus 6x equals 0. So right now I can see that I'm going to have 2 because I have a degree of 2. I can factor out a 3x. If I factor out a 3x, what I end up with is x minus 2. Now in order to solve for x, you take each piece. So 3x, set that equal to 0. X minus 2, set that equal to 0. So our possible points, if I divide by 3, 0 divided by 3 is 0. Here I'd add 2, 0 plus 2 is 2. Okay, so if I want to know the actual ordered pairs, the x is a 0, the x is a 2. To find the y, you put it back into the original. Well, if I put a 0 in here, 0, 0, this would be 5. So it's 0, 1, 2, 3, 4, 5. There's a point. At that point, the slope is 0. I know that because that's how I found that point in the first place. I took the derivative, the formula for the slope, and said, yo, that's 0. Now if I put in a 2, 2 to the power of 3 minus 3 times 2 squared plus 5, this is a 1. So if I go to the right 2, I'm up 1. That also has a slope of 0. Okay, so I know that. Now to figure out if it's concave up or concave down, I take the second derivative and it's based off of the x value. So the second derivative, put in this 0. 6 times 0 minus 6. Well, 6 times 0 is 0, minus 6 is negative 6. If it's negative 6, that means it's concave down. So where x is a 0, the curve goes below the tangent line. So this is a maximum. So we have a maximum point at 0, 5. Now I take the second derivative and I fill in the 2. I want to know what's happening here. 6 times 2 minus 6. 6 times 2 is 12. 12 minus 6 is 6. This is positive. So where x is 2, it's concave up. Okay, now that means this is a minimum. Okay, now you want your mind even blowing further? Okay, so whether you said yes or no, we're moving on to yes, we're going to do that. Okay, so I know I have a maximum and a minimum. This is concave down, this is concave up. Because it switches concavity, guess what you have to have? I know some of you said an inflection point. In order to find an inflection point, you take the second derivative and you set it equal to 0. So if I take the second derivative, 6x minus 6 equals 0. If I add 6, 6x equals 6. Divide by 6, 6 divided by 6 is 1. So I have an inflection point where x is 1. Inflection point because that's where the second derivative is equal to a 0. Well, I want to graph it. So that means I need the actual ordered pair. So I put 1 into the original function. So 1 to the power of 3 minus 3 times 1 squared plus 5, this is at 3. So if I go to the right 1, I go up 1, 2, 3. This is the inflection point. That's the exact moment where it switches from concave up to concave down. Check that out. We just did all of that by finding derivatives. I hope you feel really darn cool because by doing this, you are really darn cool. This is an inflection point. So you know maximums, minimums. You were able to sketch what that thing looked like. We did not use Desmos. You use calculus. Okay, so locating inflection points, I got excited and we did it ahead of time because you're just cool enough. I knew you could handle it. If you want to find an inflection point, you have to take the second derivative, set it equal to 0, okay? So that is what we just did in the previous one, but it is here just so that way you have it in writing. So as you're doing your assignment and you're like, how do I find that? Just go to the little part that says locating inflection points and then it will tell you. All right, let's go ahead and do this. So we're gonna put it all together. See what we can do. Step 1, we have our function negative 1/3 x cubed plus 3x squared minus 5x. Find the first derivative. 3 times negative 1/3 is negative 1, so negative x, reduce the exponent, so now it's to the power 2. 2 times 3 is 6, reduce the amount of variables, so now it's just 1. Minus 5, there's your first derivative. Second derivative, 2 times negative 1 is negative 2x, plus the derivative of 6x is just a 6. The derivative of negative 5 is 0. Okay, so I have this. Now, if I want to find possible extreme points, you take the first derivative and you set it equal to 0. So negative x squared plus 6x minus 5 equals 0. Now here, there are a few different things you can do. There is a value in front of my squared term, so you cannot jump right to multiply add. You could do the multiply add method where you found the two numbers. You take negative 1 times 5, turn it into grouping. You could do the quadratic. Or you could just say, let's divide every single thing by negative 1. X squared minus 6x plus 5 equals 0. Now I can do my normal fun multiply add. Multiply to 5, add to negative 6. Well, guess what? That's negative 5 and negative 1. So when I use this to find my x values, you take each piece separately equal to 0. So I would have x equals 5, x equals 1. So here's my possible extreme points. We're trying to sketch. Well, in order to sketch, you can't just have x values. We need to know what the y values are as well. So I go ahead and I put the 5 and the 1 into the original problem. So if I go negative 1/3, now this one is not going to be friendly. So I wanted to make sure that we did one of these that wasn't so nice together. 5 squared minus 5 times 5. Okay, I got 8 and 1/3. Okay, totally fine to get that stuff. I know a lot of times when you guys have like a solution like this is where you want to second guess yourself because it feels weird to have 5 and 8 and 1/3. So I'm telling you right now, you're going to get some weird stuff. It's okay. All right, let's go ahead and put in a 1. So if I have a 1 replacing the 5s, I got this. I hope you're doing this with me because it'd be much more fun. Oh, okay, so 1 and it's negative 2 and 1/3. So I'm going to go ahead and graph these. So if I go to the right 1, 2, 3, 4, 5, I go up 1, 2, 3, 4, 5, 6, 7, 8, and 1/3. So a little bit here, this is where my slope is a 0. If I go to the right 1, I go down 1, 2, and 1/3. This is where my slope is a 0. Okay, so that's what we know so far. Now, we want to use the second derivative to see if it's concave up or concave down at that point. So I do the second derivative, fill in the x. If I put in a 5, negative 2 times 5 plus 6. Negative 2 times 5 is negative 10. Negative 10 plus 6 is negative 4. So when x is 5, it's negative, so it's concave down. That means that this is a maximum. So 5 and 8 and 1/3 is a maximum. Okay, now I go ahead, second derivative, fill in a 1. Negative 2 times 1 plus 6. Negative 2 times 1 is negative 2. Negative 2 plus 6 is positive 4. Because it's positive, that means that it's concave up, which means that this is a minimum. So positive 1, negative 2/3 is a minimum. Because I have a maximum and a minimum, that means my concavity switched. One was concave down, one was concave up. So that means I have to have an inflection point. To find an inflection point, you take the second derivative, set it equal to 0. So second derivative, negative 2x plus 6 equals 0. If I minus 6, negative 2x equals a negative 6. Divide by negative 2, and x is a 3. but I want to know the point so I can actually graph it. So now I go ahead and I put 3 into the original function. So I'm just using my calculator. I'm just going to up arrow, change all of the 1s into 3s, and I got a 3. So this is an inflection point. This is the point where it's not concave up or concave down. It's right in between. Go to the right, 1, 2, 3, go up, 1, 2, 3. This is the point where it switches. So it's concave up to that point, and then at that point it switches to concave down. Now another thing that they said that it could be helpful. Well, what if I want to find the y-intercept? Because that's an easy point to find. Y-intercept, that means x is 0. You put it into the original. 0, 0, 0. Whoa! 0, 0. So that shows me that this is pretty darn steep right here because it has to hit that 0, 0. So that's kind of fun. So we're just taking information, trying to figure out what a graph would look like without grabbing a graphing calculator or Desmos. Okay, I tried to keep this at 30 minutes or less. I went a little bit over. I apologize, but this puts everything together. So there are some book questions. Remember, it's a suggested assignment if you're going for that notebook turn-in. There's some questions that you can look at. We also have a worksheet that goes with this section. I hope you enjoyed the first and second derivative test, and I'll talk to you guys soon.